thing I want to just a moment. If you are the in-person, if you're attending the in-person lab experiment, you might have already saw the announcement on Avenue to Learn. We will have the available time slot for you to complete your lab experiment on Saturday, and you can enter the lab and try to finish the mailment for the CBR test on Saturday morning, and the lab technicians and TAs will be there to help you collect the data. But you need to let us know whether you want to be there. If you want to join the morning session on Saturday, you should let us know, and there will be some instructions for you to enter the engineering building. You will not be able to enter through the main door. It's locked during the weekend. But for the Friday afternoon sessions, you can enter the lab. The lab technician is there, but you need to also contact us to make sure that we will have all the instruments ready for you to use. That's the only thing we want to know to prepare the or to give you the accommodation. Okay, so for the lecture today, I will work on the continue introducing the drainage design, about how to design appropriate drainage layers for the pavement structure. And so the lecture today will focus on the introductions about the criteria to select the most appropriate materials for the drainage layers. Usually for the drainage materials, especially for the pavement design, we can consider the aggregates with different grain size distribution. They could be utilized as the drainage layers or as some filtering materials to remove the water from the pavement structure. Or we can apply some geotextiles, but this one is mainly applied as the filters. It could be utilized to replace some of the aggregates, but cannot replace all their functions. The last one would be the pipes. The major purpose of the pipe is collecting the water and remove the water out of the pavement structure. And usually the pipe will be connected with or combined with the geotextiles or aggregates to build a functional drainage system for the pavement structure. I will actually go through each one of them in this class, but for this lecture, we will focus on the aggregates as the drainage layer. The figure on the right is one picture that we will cite a lot for the lecture today. It shows the grain size distribution of different aggregates, and each type of the aggregates will have one capability of the permeability. The permeability is defined as the capability of the soils to remove the water. Usually, the higher permeability will indicate that the aggregates will be able to remove the water or let the water to passing through the drainage layers faster. And this is one way for the function for us to select the aggregates. The other thing that we have considered is like we need to protect the aggregate. The aggregates will need to protect the drainage layers from clogging by utilizing them as a set of the filters, so that they can retain certain fine particles in the drainage layer. And in this figure, you can see different type of the grain size distribution, and you will find out the values about the permeability. So here, K is in this lecture, K is the variable to represent the permeability, and it could vary from a very small value, 2 feet per day. It represents the speed of the flow. The water flow can be moved along the drainage layer or the filter layer. and it could increase to several thousand or tens of thousands, depending on the grain size distribution of the aggregates. And the permeability is the one important factor for us to evaluate the how good the drainage system is. Usually, if we go to check the details about this figure, you can see that if the if the aggregates has a lot of fine particles, then usually the permeability will be smaller, especially for those lines. For the lines on the left, it has large portions of the fine particles, and what you will observe is like the permeability will be much smaller compared to the other type of the soil aggregates. But this is not the only criterion we have to consider. The way for us to identify the appropriate aggregates for the drainage layer is more complicated. That's what we're going to learn in this lecture. First, let's go to see what's the effect of the fine particles. Usually, if we try to remove the fine particles from the aggregates, we are able to increase the permeability by identifying the amount of the particles in the aggregates. We can try to get the desired permeability as we want for the pavement design. Also, if we remove too many fine particles from the aggregates, it will also have some negative impact. Usually, with less particles, the drainage layer will be less stable, and it will be easy to have some deformations, and this will potentially cause the distress of the pavement structure. So we have to find out the trade-off between the permeability and stability of the drainage layer. The table below shows the permeability of the untreated and treated asphalt treated open graded aggregates. You can find out the permeability of different grain size. For example, if you have the very coarse aggregates with the grain size of 1.5 inches to 1 inches, then the permeability would be very high, which is around 140 feet per day for the untreated aggregates. But if you add some mix this one with the hot mixed asphalt, you will probably reduce the permeability slightly to 120,000 feet per day, but still it's very high. But if you see some aggregates with a smaller grain size, say around 3/4 to 0.375 inches, then the permeability will be reduced to 38,000 for the untreated aggregates and 35,000 for the treated aggregates. It's a very huge reduction. And even if we go to see some even finer aggregates, which means that the grain size is between number 2 to number 8 sieve, which can pass number 2 to number 8 sieve, then the permeability will be reduced to 80,000, 6,000. It's a very significant reductions about the permeability of different type of the aggregates with a different grain size. And here we will also have more comprehensive comparison about the permeability with different graded aggregates. But of course, we don't consider any fine particles which can pass through number 200 sieve. So all those aggregates there will be 6 samples. They all does not have any fine particles with the grain size smaller than number 200 sieve. And you can see that with the evenly distributed particles aggregates from small grain size to large grain size, the probability would be small, around 100 for the sample 1, because it has a lot of particles with the grain size smaller than number 4 sieve. But if you try to gradually reduce the potential portions of the small or the fine particles, you can see the increase of the permeability. It could be increased from 2 feet per day to 3,000 feet per day for the sample 6. This is a very significant difference between the two samples, sample 1 and sample 6, with different portions of the fine particles. And this figure will give you more details about what's the effect of the fines to the permeability. The vertical axis shows the permeability, and the horizontal axis is the percentage of the fine particles can pass in number 200 sieve. Basically, with a higher number of the percentage, the fine particles the amount of fine particles would be larger. And clearly, you can see that by increasing the amount of the fine particles, the permeability will be reduced significantly. And you can see you can clearly see the difference about the clay materials, silty materials, and something about limestone mixed with the fine particles. They all follow these patterns about reducing permeability and the higher amount of the fine particles. To evaluate the in the design of the pavement structures, we actually have some formulas to quantify the effect of the grain size or the fine particles to the permeability. And there is one commonly applied formula, which is called the Hazen's formula. It will shows the relationship between the permeability and grain size. And here the permeability K is measured with the unit of the millimeter per second, which is similar to the feet per day. And this one shows that the permeability is a function of the effective size, which is the grain size passing through, which is the grain size corresponding to 10% passing. And in the equation, we also have the coefficient. The coefficient CK is a variable that, or the parameter that we can calibrate it from the realistic data, and usually it depends on the type of the soils that we're going to collect. Generally for the uniform sand, the effective size is around 0.06 to 3 millimeters, and the coefficient is around 8 to 12. But for the well-graded sand and the silty sand, with the effective size of 0.003 to 0.6, the coefficient is around 5 to 8. And based on these values, you can find that the permeability is much smaller for the well-graded sand and the silty sand. And another thing is like when you use this equation to do the calculation, and usually you're going to use the different type of the sieves to measure the percentage passing. You probably can find out the percentage passing through number 4 sieve, number 8 sieve, and number 200 sieve, and so on. Which means that if we can find out the percentage passing A and B for 2 grain size DA and DB, in order for you to apply this model, you need to find out the value of D10. Then you can recall this equation, the equation in this page, to estimate the grain size with 10% passing or with X% passing. So this one will just generally shows the linear relationship between the log effective size and the different percentages. So it will just under the log plot, you can try to find out the straight line between two data points, and then find out the point in between to get the grain size, effective grain size with a specific percentage passing. And you have to make sure that the percentage passing should be A smaller than X smaller than B in order for you to apply this equation. Okay, and now I will give you a simple example about how to calculate the effective grain size with the information with the percentage and the different type of the sieves that we applied in the lab. So the table here shows the percentage passing under different type of the sieves, and which means that you can find out the effective grain size with a different percentage. And we also have the in this one we want to find out the value of D10 from this example. And with that, let's see how we can use the equation we specified in the previous page. First of all, in order to call the function, which is the function I just write it down, we have log dx equal to log dA plus x minus a divided by b minus a times log dB divided by dA. And we have to make sure that a is smaller than x, smaller than b. And in this case, we want to find D10. So we need to go to the table and find out the two values which will include 10 in their experiment. So based on the sample one, we can find A should be 6 and B should be 13. So this is the percentage. The second row is the percentage passing. So we will satisfy the condition A smaller than 10, smaller than B, and A is 6, B is 13. So to do that, to solve this, to find out the value of D10, we will use this information, A equal to 6, and we have DA. DA is a number as the grain size for number 114 sieve. That value is 0.105 inches, 0.105 millimeters. And B equal to 13, and the dB is a number 60 sieve, and for that one the size is 0.25. Then we can call this formula to find out the value of D10. We have x equal to 10. So with that, we have log D10 equal to log dA is 0.105 plus x minus a. X is 10, A is 6, and B is 13, is 6 times log dB is 0.25, dA is 0.105, and with that you can get the result as minus 0.907. So we can derive the value of D10 as 0.124 millimeters. And with the value of D10, you can then find out the permeability of that material or that grain size. Actually, the permeability of this material. If you do the calculation, you will find out the value is quite similar to 10, as they showed in this table. So that's one example about how to calculate the effective grain size, which would be the grain size with percentage passing around 10. And we also has another formula to calculate the permeability with the grain size. This is a more complicated model, and this one is it's called the Mountains formula. And in this formula, the permeability is a function of three variables: the effective grain size, and n is defined as the porosity, which can be computed as a function of two variables. One is the dry unit weight, where that's the density of the soil, and the GS is the specific gravity of the soil. This is the property of the physical property of the soil. And the K is also the function of the fine particles, the percentage of fine particles which can passing through number 200 sieve, and that's the P20. And with these three variables, we can then calculate the permeability with Mountains formula. And then let's go to see the example again. Let's continue the previous example to see how we can calculate the permeability. And here we see that for the sample 1, it has 3% of minus 200 fines, which means that the percentage passing through number 200 sieve is 3%, and this one will be added to the original sample here. And we want to identify the permeability with the Mountains formula. And we also assume that the specific gravity of the soil is 2.7, and the dry density increased by 3% due to the addition of the fine particles. So then to find out the permeability, we first need to identify what information we can get, and what's the or we have to write down the Mountains formula. So first, for Mountains formula, it says that the permeability K equal to 6.214 times 10 to the power of 5 times D10 to the power of 1.478 times N to the power of 6.654 divided by the percentage passing through number 200 sieve to the power of 0.597. And the problem provides us with the value of the specific gravity, which would be GS. That is 2.7. And we also know that the dry density will be increased about 3% if we add 3% of minus 200 fine particles. So the dry density will be the original density 121 times add additional 3%. So that will be 121 plus 121 times 3%. So this is the additional 3%. With that, we have the dry density of 124.6. And we also has the percentage passing number 200. So for now, we add 3% of minus 200% minus 200 fine particles, but it will add to the 100% case. So the percentage will be 3% divided by 1 plus 3%. So this will give you the actual percentage of the fine particles with the which can pass through number 200 sieve. That is 2.91%. And we also need to find out the porosity, which is n equal to 1 minus RD divided by 62.4 GS. So we have the value of RD as 124.6 and we know the value of the specific gravity as 2.7, which will give you the result of the porosity n equal to 0.260. So we have all the variables we know for this equation. For this equation, the Mountain's formula, we know the value of D10. D10 is the one we calculated previously. That is in the previous example, we found the D10 is 0.124 millimeters, and we can then put all the values D10, P, 200, and also n in the in Mountain's formula. And I'll just skip the details about the calculation. With that, you can find out the probability k equal to 1.92 feet per day. So you can actually make a comparison about this one. Originally, if we don't have any fine particles, the probability is 10 feet per day. But if we add only 3% of the fine particles to sample 1, it will be reduced to 1.9, almost 2 feet per day. This is a very huge reduction about the probability. And this actually verifies the negative impact of the fine particles to the probability of aggregates. So this is one example to show you how we can calculate the probability based on the grain size distribution. And we also has another formula to calculate the probability, but this one is only applied for the asphalt treated base aggregates, which would be the aggregates mixed with some hot mixed asphalt concrete. With that one, the probability is a linear function of 3 variables. The PB, that will be the percentage of the asphalt cement by the total weight of the sample. And VA is the percent air voids by the total volume of the sample. And I believe if you have already attended the tutorial session this afternoon, there will be some introductions about the air void and also the weight of the sample and so on. And P number 8 will be the percentage by the weight passing through number 8 sieve. So the this will represent the grain size of 2.36 millimeters. So with this linear model, you can actually estimate the probability of the asphalt treated base aggregates. This would be in a simple model. Of course, it's also an empirical model. It comes from the calibration from the real world experiment. And so those would be the effect of the grain size to the probability. And in reality, we have, especially for the design of the drainage system, we need to think about whether how we can select the aggregates as the drainage layer or as the filter in the drainage layer. So usually we have to select those aggregates as the filter to increase the drainage area and to conduct the waterway and also to hold the in-situ soil in the place. So those would be the purpose for us to set up the drainage layers. And sometimes it could also be used as the earth dam or the embankment to support the pavement structure, especially the bottom part of the pavement structure. And sometimes it will also be utilized as the retain walls to prevent the deformation of the base and subgrade layers, subbase or subgrade layers. And usually for the filter materials, we will consider the granular soil or the geotextiles. Both of them could be applied, and I'm going to introduce them one by one. First, we will consider the granular soil with the aggregates. Generally, we need to for the selections of the appropriate aggregates granular filters, we have to consider two criteria. One is called the retention criteria, and this criteria is applied to prevent the washout of the fine particles. So we want the filter grain to must not be too coarse. It should have certain particles with a smaller size so that we can prevent these fine particles to be removed from the drainage layer. With that, we can make sure that the drainage layer is stable. So that's one condition. The filter grain must not be too coarse. And the second condition is like we should have some permeability condition criterion, which means that we want to drain the water and build up of the pore pressures to remove the water as fast as possible. And this also indicates that we should not have too much fine particles. And if the percentage of fine particles is too high, it probably means that the permeability is low, and this will give us the second criterion. The filter grain must not be too fine. So these two are actually conflict with each other. But in this selection, we need to find out the trade-off between these two criteria. So from the previous study, we actually have found out the general criteria, the general conditions for the retention and the permeability criteria. First of all, the retention criteria, we want the effective grain size at 50% passing for the filter materials should be smaller than 5 times the effective grain size of 85% for the soils. So we usually define the first one, D15 filter, as the average filter pore size, and this would be the the D85 will represent the properties, the grain size for the soils. And for the permeability criterion, we want the D15 filter to be higher than 4 times D15 soil. So with these two, you can actually find that for the D15 filter, it should be higher than 4 times D15 soil and smaller than 5 times D85 soil. So this is the what you may have some questions about what is the filter, what is the soil. So the filter basically considers as the drainage layer. So this is also the drainage layer. And the soil would be the part immediately behind the drainage layer. So that's the definitions for the soil and the filter in the selections of the drainage materials. And those would be the two major criteria, the retention criterion and the permeability criterion. We also have another criterion, which is trying to make sure that the grain size distribution for the soil and the filter was to be parallel to each other. With that, we will have the third one. So this is the first one, second one, and third one. We will have the value of D50 filter smaller than 25 times D50 soil. So those three criteria will be applied for us to select the to identify whether one aggregate is appropriate for the drainage layer. And also the from the researchers mountain, they recommended that the amount of the fine particles passing through number 200 sieve should not be higher than 5%. If it's higher than 5%, then we need to remove the some portions of the fine particles from the aggregates. And this is also equivalent to the D5 filter to be larger than 0.0029 inches or 0.074 millimeters. So those would be the criteria we have to consider. And but usually for the highway design, we will have a different criterion, a little bit slightly different. For the permeability, we want the ratio between the D15 for the filter and the soils be higher than 5. But for the from the previous page, that will be 4. And for the retention of the clogging criterion, that will be the D15 filter divided by D85 soil should be less than 5. This is consistent to the general criteria. So that's only applied for the highway design. So it's a slightly different, but in general they will be similar. So to summarize the criteria, usually we want in the real world design, we want to make sure that the ratio between D15 filter and D85 soil is smaller than some value between 2 and 4. And for the permeability criterion, D15 filter divided by D15 soil should be higher than some value between 4 and 5. And in that case, you can actually see what's going on here. For example, if we have if we know the grain size distribution of the soil, which would be the blue line here, you can then identify the value of D85. Say that is 0.11 millimeters. You can also find out the value of D15 for the soil, that is 0.009 millimeters. Then we can identify the possible ranges about the filter materials. First, if we go to check the permeability criterion, you have D15 filter should be larger than 5. Say that 5 times D15 soil. So in this case, that will be 0.045. So it should be higher than this value. Just keeping in mind that for the horizontal axis, right side means smaller value, right side means larger value. So larger than this one means that go to this direction. And we also know the value of D85 soil, which is 0.0 or 0.11. From the first one, we can then find that the D15 filter should be smaller than 5 times D85 soil. And in this case, that will be 5 times D85 soil, that is 0.55. If we put a 0.55 in this graph, and you can find that D15 filter should also be, this is the line for the 15, should also be smaller than 0.55. So it should also be this in this region. So if we combine these two, this would be the suitable region for you to select the filter materials. And for the effective grain size at 15% pressing, it should be between 0.045 and 0.55 millimeters. So that's the general way for us to narrow down the materials that we can use. So with that, we have finished the introduction about the criteria we're going to use. And then let's go through one example to see how we can identify one or determine whether one material is appropriate as the drainage layer. In this example, we see that we have one material with the permeability of 20,000 feet per day, and that's generally 70 millimeters per second. And it will show us in this figure, which would be the this line with 20,000 feet per day. And we know that there's a soil with a certain grain size. D15 is 0.0013 inches, D50 is 0.0055 inches, and D85 is 0.021 inches. We want to determine whether this soil, this this aggregates, this open graded base, which would be this one, is appropriate. Is an appropriate filter material for this type of the soil, with these three values. If not, what kind of filter materials do you think along all these filter materials? What kind of materials do you think is appropriate as the filter material? So that's the problem. With that, let's see how we can solve this problem. Let's see how we can solve it. I probably cannot finish all of them today, but I will try my best to provide at least solve the first one, whether the open graded base is appropriate. So first, we know that for the filter materials, that is 20,000 feet per day. So we're going to choose this line. And then we want, in order to identify whether this one is appropriate, we need to find out the value of D15 filter and D50 filter. So from this figure, it's actually this is actually one experiment. The lines actually comes from the lab experiment, so we can know the percentage at some specific sieve size, which was shown as the horizontal axis. And we want to find out the percentage passing through with the grain size with 15% passing. That one will be some location here, but we do not know the exact value. Also, we want to know the some place passing through 20 or 50%. With that, we can actually go to see the this figure is not quite clear, but I can list all the values for you. So basically, in this line, we can find out the percentage of, say that the percentage of 1, that would be the smallest one, and the next one is 32, with the size of 0.19, the 32 with a size of 375, which is number 4 sieve, and 8/3 inches sieve. So with this one, you can see that this could be A and this could be B. A smaller than 15 and 15 smaller than B. So we can then calculate the value of D15. So log D15 will be log D1 plus 15 minus 1 divided by 32 minus 1 times log D32 divided by D1, and we know that D1 is a 0.19, and it's 14 divided by 31 times log D32 is a 0.375, D1 is a 0.19, and then we can find out the value about log D15 as minus 0.588, and that will give you the value of D15. This is for the filter material, so I just put in the filter here. The value is 0.26 inches. So that's the value for D15. We can apply the similar procedure to calculate the value of D50. So for D50, we will then need to go to check the another two values. One is about actually you can find out the value of 0.5. This is a half. So 0.5 inch and 3/4 inch. So at dA equal to 0.5, we have the percentage parsing as 0.47, and dB equal to 0.75, then B equal to 66. It's not quite clear for you to, it might not be quite clear for you to see this through this figure, but you can, after class, you can try to make the figure larger and you can try to observe the value by yourself. And then we can apply the similar function log D50 equal to log D47 plus 50 minus 47 divided by 66 minus 47 times log D66 divided by D47, and this will give you the value as minus 0.273, and that will give you the value of D50 filter equal to 0.53 inches. So we have this information, and now we need to determine whether this material is appropriate for the filtering material. And we have D15 filter equal to 0.26. We have D50 filter equal to 0.53, and we have D15 soil equal to 0.0013, D50 soil equal to 0.0055, and D85 soil equal to 0.021. And with that, we can then check whether it's appropriate. So there will be 3 criteria. The first one is the retention criterion. So that will be a D15 filter divided by D85 soil. So this one is 0.26 divided by 0.021, that is 12.4. And clearly this one is higher than 5. So if it's higher than 5, we have to make sure that for the retention criteria, this ratio should be smaller than 5. If it's higher than 5, it means that it's not appropriate. We can also go to check the permeability. That will be a D15 filter divided by D15 soil. So the value is 0.26 divided by 0.0013, which is 200. This is higher than 5. And this actually satisfies the permeability criterion. So this should be okay. And we have the additional criterion for the parallel grain size distribution, requires the D50 filter divided by D50 soil. So in this case, we have 0.53 divided by 0.0055. That is 96.4, which is higher than 25. For the additional condition, the third condition, it should be less than 25. So in this case, it's not appropriate. So we say that these aggregates, the answer for this aggregates is no. So this aggregate is not appropriate for the filtering material. There's a second question, and we don't have time today. So I will go through them tomorrow, and we will have an additional analysis about how to select an appropriate filtering materials for this specific soil. Okay, I think that will be all today. I'm sorry that it get 1 minute longer. Do you have any questions so far? Okay, if we don't have any questions, I guess that will be all about the lecture today. And just feel free to let me know if you have any additional question. And I will also let me know that if there's any problems about the lab report, lab experiment, we need to finalize the schedule as soon as possible. Okay, I think that will be all today. Thank you very much for your time. And if there's no question, I will close the meeting and I'll see you next week. See you tomorrow.